Okay, so welcome to lecture 10. This week we're starting on a new topic, and the topic is called Brownian motion. So the idea behind Brownian motion is that it's quite closely related to the random walk, but we want to consider something what we call a continuous time version of the random walk. So to do that, I'm going to start by talking about rescalings of random walks. Then I'm going to give you the definition of a Brownian motion. I'm going to talk about some interesting behavior that the Brownian motion has, the reflection principle, which is something that we saw for the random walk, and we'll show that similar kind of ideas hold for the Brownian motion. And then I'm going to talk about the distribution of the running maximum. This topic of Brownian motion, I'm splitting across 2 weeks. So this week we're going to talk about some properties and kind of have a little bit of an introduction to some of these distributional properties and so forth. And then next week, I think I will talk more about some distributional properties and other interesting properties of Brownian motion, but I'll probably spend a good portion of the lecture showing how to construct and show that a Brownian motion actually exists. Okay, so I decided not to do that this week because it's kind of just jumping into some quite technical stuff straight away, and I thought it would be better just to try to get a bit of a feel for Brownian motion before we actually get into proving that it exists. So the idea behind a Brownian motion is that we can view it as an infinitesimal random walk. So the idea is a random walk, as we've seen in previous weeks, it takes integer time steps. So basically every time step occurs 1 unit of time later. And the random walk that we've seen so far has pretty much been like the standard random walk where you take a unit step upwards or a unit step downwards. And that random walk is mathematically really interesting and has lots of applications and the Markov chains and all that. But when we think about modeling, for example, things like share prices or things like that, the randomness that we see does not take, the share price does not update every 1 minute and does not go up by $1 and down by $1. We want to develop a mathematical tool that allows us to model those types of phenomena. Phenomena that the movement occurs in a very small amount of time, and those movements, they take upwards and downwards movements, but which are not necessarily unit, but are going to be normally distributed movements up and down. So the topic of Brownian motion is quite interesting because I'm using the words here Brownian motion, and this comes from a biology context where a guy called Brown, a surname Brown, he observed in his microscope that pollen moved around, like very, very small bits of pollen moved around in water with these kind of random movements, and as they bump into each other and kind of move around. So that was when it was first experimentally observed, this Brownian motion. And in fact, Einstein used this concept of a Brownian motion in the early 1900s, and he used that concept for physical phenomena, some physics theory. But it wasn't until I think it was like early 1920s that another mathematician actually showed that you can prove that such a process exists, and that was quite an achievement, and it's been really a cornerstone of probability theory and stochastic process theory since then, and it's been used heavily in mathematical finance for option pricing, like the Black-Scholes model comes from Brownian motion, and a whole bunch of other things. So it's a very important process, and it's one of the core processes that you use inside stochastic process theory. So the idea is that let's just think about a random walk. So as we've seen before, random walk is this process Sn, which is given by the sum of these increments, x1 up to xn. The increments are IID, and we've typically seen the case where the increments take values in -1 or +1. and we've seen that these random walks, if we assume that there's that it's a simple random walk, so that the positive movement and the negative movement have equal probabilities, the probabilities of a half, then we have the expected value of Sn is equal to 0. Now, to show, to kind of work towards this concept of Brownian motion, there's a first lemma that we might want to consider. That is, the random walk Sn is a martingale, and in fact we've kind of seen that before. But the other property is that the covariance between Sn and Sm, where n and m are two integer time points, is equal to the minimum of n and m. Okay, that's kind of easy to show if we use conditional expectations and filtrations. So the covariance of Sn and Sm is just, we just write down the formula for a covariance. And then, since the expected value of these things are equal to 0, this whole term here disappears. And then, using the Tower property of conditional expectations, we can introduce this filtration up to the time point m wedge n, which is the minimum of m and n. And this just holds by the Tower property of conditional expectations. So we can basically introduce an inner this inner conditional expectation. Now we can, since this is the filtration up to time point, which is given by the minimum of n and m, this pretty much means that if whichever is smaller than the two, that's the time point up to which we freeze the, in some sense, the random walk, and we can pull out the part of the random walk which is frozen up to that point, which is the s and the minimum up to time point and the minimum of m and n. And then the other part is this, we leave it inside the conditional expectation, but which is the maximum of m and n, whichever one of these is maximum. And this allows us to use the martingale property, so that when you have something like this, and since the random walk is a martingale, we pretty much have then s up to the minimum of m and n, and so we have this times the same thing again, so we get a squared there. But that is just, since the mean is equal to 0, that's just equal to the variance of that, and then the variance of that is just equal to the minimum of m and n. Okay, and that's going to be an important property, and something that a property that we're going to see when we consider Brownian motions as well. Now, the interesting property of random walks is that as a result of the independence of the increment random variables, if we have I less than or equal to j and k less than or equal to L, such that I and j are strictly less than k and L, then the increment Sj minus Si is going to be independent of the increment Sl minus Sk. That basically means non-intersecting kind of time increments are going to be independent of it. The random walk's going to be over those time increments is going to be independent of each other. Okay, this basically means that if we take some time interval and break it up into a sequence of times between 0 and in, so you can kind of think about this as being a mesh of time points. So you can kind of think about it being something like you have time like this, and you kind of break it up into a mesh like that. Then the difference of the random walk over, so the increment of the random walk over consecutive time periods is going to be independent of each other. The other interesting property of the random walk is that if j minus I is equal to L minus K and is equal to, and that number is equal to that number, which is equal to M, then the distribution of the increment Sj minus Si is equal to the distribution of the increment of Sl minus Sk, which is also distributed like just Sm. Okay? And this basically means that the random walk has stationary and independent increments. Okay, so these are nice properties, and we want to think about Brownian motion as an infinitesimal version of the random walk. So what we want to do is we want to kind of take the time interval between movements as delta t, and the increments between the spatial increments of the random walk to basically get smaller and smaller. So you can kind of think about, we have a random walk and it's taking integer time steps, and then we want to make those time steps over the same long increment like that. We might want to make them even smaller, something like that, and then even smaller. And then as we do that, we want to make the spatial increments that it has as well kind of very small. Okay, so instead of just taking increments, positive and negative increments of plus or minus 1, we want to be able to take them very small kind of spatially as well. So you can kind of think about these delta x's as being in that direction, and then the delta t's as being the time increment. So, and we want to make those limit to 0. Now, using the central limit theorem, we can already start to explore what happens. So, as we know that the mean of the spatial increments is equal to 0, and if we and the variance of these increments is equal to 1, and we take that to be just equal to sigma squared, and we take delta t to be 1 over n and delta x being 1 over the square root of n, then as you see, as n goes to infinity, these delta t's become small and the delta x's become small. What it also means is that if we rescale, we don't have to, if we use like a central limit theorem, we don't actually have to take off the mean there, and then we kind of divide by this spatial scaling. Then this quantity here, the probability distribution of this as n goes to infinity approaches like this standard, the CDF of like a standard normal. More generally, it holds that if we take a random walk and then consider the integer part of n times t, and then, which is denoted by that, we get the same thing as n goes to infinity, that we get the CDF of a standard normal. What this means is that if we kind of rescale the random walk this way, that the time increments are given by 1 over n and the spatial increments are given by 1 over the square root of n, then as n goes to infinity, at time t, the net gain, the spatial gain at time t is going to be normally distributed with mean 0 and variance t. Okay, and we can see that by the t in there and there. Okay, so that kind of gives us the viewpoint of a Brownian motion as kind of like a rescaled random walk. Next week I'm going to show you a proof, which is a slightly different way to tackle this, and will give you a more complete and technical proof of why Brownian motion exists. But we can for this week, we can just pretty much take the viewpoint that we just define a Brownian motion, and we don't need to construct it. We're just going to define what it is, and then next week I'll show you that if we have that definition, we can actually prove that such a process does actually exist. Okay, so let's talk about the definition of a Brownian motion. So we're going to let omega fp to be our probability space, and we're now going to define a continuous time stochastic process. So this is something we haven't done before, and that is, instead of letting our time parameter be integers like 1, 2, 3 and all that, we now allow our time parameter t to be a positive real number. Okay, so this means that it's a continuous time stochastic process. So as for any time t that we choose, which are a positive real number, the process is going to be defined. Okay, so the definition of the Brownian motion as follows. It's going to be a real valued stochastic process, and we're going to call it Wt, and we call this process a Brownian motion. It's also called a Wiener process because Wiener showed that it actually mathematically exists, and this is why Brownian motions are often denoted by a W, like Wt, but you can use other things like xt or bt or anything like that, whatever you want to call it. And so we're going to call this process Wt, a Brownian motion if for some constant sigma, some real constant, that under the probability p, that it has 4 properties. Okay, and the 4 properties are as follows. So for s and t, the random variable given by the increment Wt plus s minus Ws, this increment has a normal distribution with mean 0 and variance sigma squared t. And you can see here, if you take sigma equal to 1, you can see that we're kind of getting the similar behavior that we got with the rescaled random walk. Okay, and 2, for each n and times t0, t1 up to tn, such that all these times are less than or equal to each other, then the random variables given by the increments wtr minus wtr minus 1 are all independent of each other. Okay, so every time you take a small time increment between, say, t0 and t1, then that little increment compared to the other little next increment, those 2 random variables are going to be independent from each other. 3, the Brownian motion at time 0 is equal to 0. And 4, the Brownian motion is continuous in the t variable. What that means is that you can kind of draw a Brownian motion without lifting your pen. So it's going to be this random process like this, which doesn't have any gaps in its path. So that would be one path. That could be a different path of it, and so forth. Okay, so it's going to have paths like that. I'm drawing it this way because the process starts at 0, and as you move further away from 0, the distribution of the paths is going to be related to t. Okay, it's going to be proportional to t, right? Because we said that any increment is going to have variance sigma squared t. Okay, so that means the closer to the origin you are, the more concentrated around closer to 0 it is, and as you kind of move further away, it gets more and more dispersed away from 0. Okay, so if we consider this definition, there's a few remarks to make about this definition. The first remark is that the properties 1 and 2 that the process has to have basically means that the Brownian motion has stationary and independent increments, similar to the rescaled random walk, as we talked about before. This property here that the Brownian motion starts at 0 is equal to 0 at time 0. This is more of a convention than anything else, and it's not a necessary property of the Brownian motion, but I guess it's just a nice convention to have. If you need the Brownian motion to start anywhere else, you can just always add a constant. So you can look at a Brownian motion plus a constant. Okay, so it's kind of like the canonical Brownian motion starts at 0. And property 4, that the paths are continuous in time. So property 4 is actually an important one, and it's actually it's a consequence of the previous 3. In fact, the definition given by just the first two properties, that is in some sense the definition that Einstein used when he was kind of doing his physics calculations. But the property number 4, that the Brownian motion has continuous paths, this is in fact what Wiener did, and this is his major contribution, and showed that a process with continuous paths and the properties above actually exists, and that was kind of a major contribution to the mathematical literature. As a kind of an interesting side story, so this was Wiener, so this was kind of like early 1900s, like probably around the 1920s. And when Wiener finished his PhD, and shortly after his PhD, he applied for a job at University of Melbourne, and he actually didn't get the job. Someone else got the job. And I think he ended up at MIT, and then he kind of built this amazing theory that's still used like 100 years later and all that. So it's kind of a bit of a failing of University of Melbourne not hiring him, because he would have been a great guy to have on the faculty. Anyway, so the definition of a Brownian motion, well, so if we take, so this definition had this constant sigma in that, so that's just a Brownian motion. The one that people typically use is the standard Brownian motion, and that is a process with sigma squared is equal to 1, and we'll just call that the standard Brownian motion or Brownian motion. So typically when I talk about a Brownian motion, I'm just going to assume that sigma squared is equal to 1. Okay. Now, if we combine properties 1 and 2 here above, so these two properties, we can actually write down, in some sense, like this, the conditional distribution of the Brownian motion at time Tn, given the Brownian motion at n other times. So I is going to be integers between 0 and n minus 1. Okay, so condition on a whole bunch of other time points that this distribution is just basically given by the distribution of the increment of the Brownian motion. So if we condition the Brownian motion up to n minus 1 at kind of these n minus at Tn minus 1, okay, so then the increment past that, so this distribution is given by the increment from Tn minus 1 to Tn. Okay, and that can be explicitly written out in terms of a CDF like that. This, in some sense, if you can kind of think about what's inside there, where we've kind of plugged in a the t and the x and the y and so forth. We're going to call this this p here, this transition density. So instead of writing it out in terms of this all the time, I'm just going to use this standard transition density. What that means is that we can, for time points t0, t1 up to tn, and writing x0 is equal to 0, then we can basically write out the joint density function of the Brownian motion at time points t1, t2 up to tn. And it can be explicitly written out in terms of this transition density up here, where we plug in for the time, just the time increment, and x here is going to be the previous time step, and xi is the current time step, and we have the product of all of these time steps. Okay, so it basically means, and this is what we're going to call the joint distribution of the Brownian motion at n time steps for all possible time steps is going to be called the finite dimensional distributions of the process. Okay, so maybe I should draw a picture. It basically means that we're basically, these finite dimensional distributions are, we kind of look at the Brownian motion at that time step, say at various time steps, and they don't have to be uniform, and that all of the distributions here, sorry, bad drawing here. Okay, and these are going to be the finite dimensional distributions of the process. What's nice is that all these finite dimensional distributions, you can see that they're going to be normal with varying parameter for the variance related to time. Okay, so the first lemma that we have is that if we consider the increment of the conditional expectation of a Brownian motion, where we look at the increment past, so let me draw this. So if we consider a Brownian motion up to time s, and then have some other time point t, that we have the Brownian motion path up to time s, and then the path given by between s and t, the conditional expectation of that increment of the path is conditioned on the pink part. So we have so this is the pink part, and this is, in some sense, the green part here. The conditional expectation is going to be equal to 0. The other property is the covariance between two time points, ws and wt, is just given by the minimum of s and t. Okay, and so this is the property that was the random walk had it, right? Okay, so I'm going to leave that as an exercise or for a tutorial or something like that, because it's just kind of interesting to go through yourself, and involves a bit of calculation, which I feel is like a little bit boring for a lecture format. And the other nice property is that since these finite dimensional distributions are all going to be normally distributed, and in fact it's all going to be a large multivariate normal distribution, and those are determined by its means and covariances, and normally distributed random variables are independent if and only if their covariances are 0. This is a very special property of normal distributions and multivariate normal distributions. This, combined with the continuity of the paths, basically characterizes the standard Brownian motion. Okay, so what I'm basically saying is that the fact that this process has normally distributed increments and continuity of paths makes the Brownian motion very special. In fact, if you kind of relax any of those properties, for example, you decide to say, okay, the distribution of the increments is no longer normal, it's some other distribution, then you pretty much lose continuity of paths, for example. Okay, so So the Brownian motion is a very unique process in the fact that it has continuous paths and these probability increment distributions being normal. Okay, so again, yeah, it's a very special, Brownian motion is a very special process. It is, in fact, so special that it actually has a lot of really strange and kind of unique behavior. So, for example, we say that the paths of Brownian motion are continuous, and at first thought, one might expect that since the paths of the Brownian motion are continuous, they might be kind of quite well behaved and quite nice. But in fact, so continuity of something is very nice, but the Brownian motion has a lot of really strange properties. For example, even though the paths of the Brownian motion are continuous, they are so rough that they're actually differentiable nowhere. Okay, so if you've done some mathematics, you know, differentiability of some function basically means that there's some kind of a smoothness to the function. You should think about paths of Brownian motions as being kind of like functions, and the Brownian motion is in fact so rough and so jagged, the paths, that nowhere are they differentiable. Okay, so just think about that. That's kind of a really strange property of a function, that it's nowhere differentiable. Okay, you can't even find a small part of the path of the process that is differentiable. Okay, so you might have considered paths. You might have considered functions which are not differentiable at a point before, or something like that. But here you can't even find like points or little tiny segments of the path that are differentiable. That's how rough it is. The other interesting property is that it doesn't matter how you scale the paths, they always look the same. So this means that if you take a path of Brownian motion and you kind of zoom into the path really closely and you look at it, it's still not going to be differentiable, and then it's going to look really rough and like a Brownian motion. And then if you zoom in again, even further into the path, then it's still going to look like a Brownian motion. And you know, you can keep on zooming into the path of the Brownian motion, and it's always going to look the same. It's always going to have these jagged paths and all that. So what's interesting is basically this means that the Brownian motion is a fractal. Okay, the paths of Brownian motion are fractal paths. The other interesting property is if you choose any number, what's going to happen is that the Brownian motion will eventually hit that number, no matter how large or small you choose that number to be. If you wait long enough, the Brownian motion will hit that number. Now, that in itself is kind of interesting, but the really weird property of this is that once a Brownian motion hits its value, then it's going to hit that value again immediately and infinitely often. Okay, again, this is due to this fractal property of the path of Brownian motion. It's going to hit it infinitely many times after that as well, and it will also continue to return to that after arbitrarily large times as well. So it will hit it again very quickly. Then the path of the Brownian motion will move away from that point, and then it would typically come back to that point. If you wait long enough, it will always come back to that point. Okay, so as I said, the fact that such an unusual process exists is actually quite strange, and this was only proved in like 1923 by Norbert Wiener. Okay. There are many different proofs of the existence of such a process. Some are pretty technically difficult from a mathematical perspective. Next week, I will show you a kind of quite an intuitive construction of why such a process exists, which I like. The reason I like that this proof is because it kind of gives you a bit of an intuition about how to actually simulate on a computer as well. Okay, so now that we've defined a Brownian motion, I'm not going to get into the proof of the existence of a Brownian motion, at least not this week, but I want to start to look at some of the properties of Brownian motion. And I want to show you that some of the nice properties that we saw for random walks also hold for Brownian motion. So the first thing that we should know is that the Brownian motion is a process without memory. That is, if you consider the Brownian motion at some time t and another fixed time s, then the increment of the Brownian motion past the point s is going to be independent of the Brownian motion path up to time s. Okay, so if you have path up to time s, then the increment of the path past that is going to be, this part is going to be completely independent of that part. Now this is for some fixed time s that we set in advance before the path of the Brownian motion sets off. But this is also true if we consider this property at some random time tau. Okay, so remember these random times are, we might not know them until they actually occur, as opposed to setting some fixed time before the process starts off from zero. So this is quite a strong property of the Brownian motion, that basically at some random time, the process past that random time, the increment of the process past that time, is again going to be a standard Brownian motion independent of the Brownian motion up to that random time. So we've seen random times before with Markov chains and random walks, and a particular type of random time that we've seen is a stopping time. Stopping times exist for continuous time processes as well. They're a little bit more technical. I won't get into the deep proofs of stopping time proofs for these continuous time processes, but I'm going to kind of keep it a bit more of the intuition level. But the intuition is very similar to random walks. And we say that a stopping time tau for the Brownian motion is going to be a random time such that for each t, the event that tau is less than or equal to t depends only on the history of the process up to and including time t. This basically means, this definition basically means that if you observe the Brownian motion up to some time t, this means that we're going to be able to determine whether or not tau has actually occurred. Okay, so one of these proper stopping times means that if you're at time t, you should be able to determine if that random event or that stopping time has occurred or not. Okay, so stopping times are going to arise in the context of hitting times. We've seen hitting times for Markov chains and random walks before, and we have the same concept for a Brownian motion. Okay, so we're going to set some fixed level A, and we define the hitting time of A as tau A, and it's going to be the minimum or infimum time t such that the Brownian motion hits A, level A. Now, if the Brownian motion does not hit A, we're going to set tau A to be equal to infinity by convention. So it's quite easy to argue that this tau A that I've defined here is actually a proper stopping time by the continuity of paths of Brownian motion. Okay, so these continuity of paths are going to come up again and again with a lot of proofs around Brownian motion, and it's a powerful property of Brownian motion. So by continuity of paths, the event that tau A is less than or equal to t is basically equal to, has the Brownian motion hit A for some time s where s is less than or equal to t. And this only depends of the Brownian motion up to time t. Okay, so this is in some sense the only way that stopping time can occur, right? And it has to, since the paths of Brownian motion are continuous, it has to kind of hit it continuously, right? And go through that, hit that level and pass through it in a continuous manner. Again, by continuity of paths, if tau A is finite, that basically means that the Brownian motion at the time tau A is equal to A, exactly. Okay? And this is again due to continuity of paths. Now, I can give you a counterexample that you should think about in terms of stopping times, because you might say, well, is every random time a stopping time? Well, in fact, no, because you can think about quite natural things to define. For example, the last time that a Brownian motion hits level A is a random time, but it is not a stopping time, because at time t, you cannot determine if Brownian motion, if this is the last time that Brownian motion has hit this level, right? As I said, Brownian motion is a kind of interesting process, because no matter what level or value that you choose, you can wait for some time, and at some time point later, it could be a very, very long time, a waiting time, but the Brownian motion will return to that point. And that means that the last time at which the Brownian motion hits that level is, of course, going to be a random time, because we don't actually know explicitly what it is, and it's going to be random for every path. It's going to occur at some different random time. But it's not a stopping time, because at time t, we can't actually determine that last time, right? Because that random time does not depend on the history of the process up to and including time t. Okay, so similar to the random walk, there's lots of symmetry in paths of Brownian motion, and we can exploit that symmetry to find a relationship between the distribution of the stopping time tau A and the distribution of the Brownian motion at time t. Okay, so this is a first nice little result about Brownian motion. That is, if Wt is a Brownian motion, again, by convention, it starts at 0, and let A be some level that we choose. Here I'm going to choose it to be a positive level. Then the probability that tau A is less than t, so the distribution of tau A, is equal to 2 times the distribution of the probability that Wt is strictly greater than A. Okay, so it basically gives the distribution for tau A in terms of the kind of exceedance probability of the Brownian motion. So the proof goes as follows. So if the Brownian motion at time t is greater than level A, okay, so I can draw my diagram here. Suppose at t, so at that time point t, it is above level A, which I'm going to denote by this level there, A. That means that by continuity of paths, the only way it could have got up to this level is if it actually went through this level here, A, right? Because the paths are continuous, it has to go through that level A at some time point before t. Okay, and that basically means that tau A is before t. And since tau A is a proper stopping time, then the increment of the Brownian motion past, it's a bit of a typo, that should be tau A. So the distribution of the Brownian motion past this increment, past time point tau A, is going to be a Brownian motion in itself. Now, by symmetry, since this is again a Brownian motion, it has normally distributed increments, then the probability of this increment being greater than 0, given that tau a is before time t, is going to be equal to a half. Why is that true? Well, because it's going to be normally distributed, and we know that this is going to be from tau a onwards, it's going to be centered at 0, this normal distribution. And so half of the distribution is going to be contained in the probability that it's in the upper part of this distribution is equal to a half, because the probability, because of the density under the whole normal curve is equal to 1. Okay? So that means that the probability of Wt strictly greater than 0 is equal to the joint probability of tau a less than t and Wt minus W tau a greater than 0. But these two events are, so this kind of using a Bayesian type formula, we can write this joint distribution in terms of a conditional distribution and this tau a less than t. But this increment here is what we have up here, this conditional probability, which was equal to a half. So we just substitute that half there. And then we leave this tau a less than t. And then basically you multiply both sides by 2, and we have our result. Okay, so that's the proof of that result. And it shows this really nice relationship between this stopping time of hitting the level, the hitting time, and the distribution of the exceedance distribution of the Brownian motion. So you can actually take this idea further, and you can get the following lemma. Again, I'm not going to prove this now, and I think I would probably leave it as an exercise, or maybe for a tutorial or something like that. That is, if the Brownian motion is a standard Brownian motion and tau's a stopping time, it could be a hitting time, but it could be something else, then if I define a new process called tilde Wt, and this process is given by the original standard Brownian motion up to time tau, and given by 2 times w tau minus Wt for t strictly greater than tau, then this tilde Wt is also going to be a standard Brownian motion. So how do you prove such a lemma? Well, in fact, you just need to go back to the definition of a Brownian motion, and you need to kind of check that these 4 properties hold. And when you, for this new tilde Wt, you should be able to prove that all of these 4 properties hold. And if you can do that, then you've basically shown that it is a Brownian motion as well. Okay, so what does this process actually give? The intuition is kind of quite nice behind this, and that is if you actually take this tau here to be the hitting time of level A, there, and this is the time tau A, what this new process is doing is that for t less than or equal to tau, then the two processes, Wt and tilde Wt, kind of share the same path. So it's the green and the magenta paths are over the top of each other because they're equal to each other. But at time tau a here, what's actually occurring is that this here is flipping around the process and basically giving a mirror image copy of the Wt. So you can kind of think about this as being a mirror in between here, the level A, and so the tilde Wt is the mirror image of the original Wt. And then because of these properties of the increments are going to be normally distributed, you have this kind of really nice kind of symmetry between these mirror copies. So the final property that I'm going to show is and again, I'm trying to keep this as a kind of a short lecture to not overwhelm you with a whole bunch of stuff. We're getting to the end of semester, so I kind of just want to slow down a little bit and not finish off with a jam pack full of new results. So the final result I want to show this lecture is that it is also possible to show various interesting joint distributions of statistics of Brownian motion paths and Brownian motion. So some interesting statistics are things like the running means up to the current time, things like a running maximum or running minimum, or I mean, you can dream up a whole bunch of other things like this, but the key point is that they are the running ones. So it's the maximum up to time t. It doesn't mean it's the global maximum of the process. It's just the maximum of that process up to that time t. Okay, so the lemma is, if we denote by mt, the running maximum of the Brownian motion up to time t, then for level A strictly greater than 0 and A greater or equal to x and all positive times, then the joint distribution of the running maximum of the Brownian motion being greater or equal to A and Wt being less than or equal to x is actually given by 1 minus the normal CDF evaluated at 2a minus x over the square root of t. Okay, so let's prove this result. So since mt is the running maximum of Brownian motion, and the Brownian motion starts off at 0 at time 0, of course, if the Brownian motion goes negative, then the running maximum during all the time that the Brownian motion goes negative is going to be equal to 0. And if it goes positive, that means that running maximum will also increase. So it's kind of logical that the running maximum is going to be greater or equal to 0. It's also going to be non-decreasing in t. So it either stays at the same level, at the same value, or if the Brownian motion goes and hits new heights, then that running maximum is going to increase, but it can never decrease. So once you've hit a level, that's the running maximum is going to stay at that level, and so that means that the running maximum is non-decreasing in t. If we define tau A as being the hitting time of the Brownian motion, hitting the level A, it also means that the running maximum, the event that the running maximum is greater or equal to A, basically means that the Brownian motion has to have hit a level A at some time point before time t, right? Because it's the running maximum. And so that basically means that this event is equal to tau A less than or equal to t, right? Because this is the time at which the Brownian motion has hit level A. Now, using the reflection principle, which is the previous lemma here, we have for A greater or equal to 0, A greater or equal to x, and t greater or equal to 0, that the joint distribution of mt greater or equal to A, Wt less than or equal to x is equal to the probability of tau A less than or equal to t, because of this here, and then jointly with Wt less than or equal to x. But using the this representation here, taking tau to be that hitting time, we have that this is equal to this. But if the tilde Wt is greater or equal to 2a minus x, that basically means that the tilde Wt has hit level A before time t, and also Wt that has occurred. So that means we can write this line as that line there. Okay, Now this here, this is a standard Brownian motion. And so we can just write this, just doing a transformation, we can write that in terms of, so it's a standard Brownian motion with variance t. And so we can write this probability in terms of 1 minus the normal CDF evaluated at 2a minus x over the square root of t. Okay, so we basically have that joint distribution has this explicit probability that we've determined. So we finished the lecture with the following proposition that I'm just going to state because I think these are kind of interesting exercises to go through in tutorials and so forth. And the proposition is as follows. So if Wt is a standard Brownian motion, then if you take this process and multiply by c and then rescale time by c squared, so t over c squared, that this is also a Brownian motion. So kind of rescaling the Brownian motion this way also gives a Brownian motion. If we do something similar, but this time we consider the Brownian motion multiplied by t, but we take time to be 1 over t, under the condition that we take this to be equal to 0 when we take t is equal to 0, because we don't want that to become infinity, then this is also a Brownian motion. And if s is some fixed time, then this is also a Brownian motion. Okay, so these are really 3 interesting properties around Brownian motion. And again, to prove these results, you pretty much have to go back to the definition and prove that all those 4 properties hold. And then basically, these are just some really standard transformations of Brownian motion that are useful and that give back Brownian motions. Okay, so that's the end of the lecture for this week. And then a lot of these properties I think we'll do in the tutorials and potentially workshops. And yeah, so next week I'll prove the existence of Brownian motion, and I'll show you a few other interesting properties of Brownian motion. Okay, so I'll see you all at the workshop.